so where he's presently a postdoctoral scholar working with Professor Graciela Gelmini, and she's a well-known phenomenologist and also theorist, and he's not directly working, but that's like a close group there also with Professor Alexei Kushenko, and he's also well known for all non-WIMP dark matter candidates, and also if you have read the SNOMAS reports for that group, I think CF6 or 5, he's one of the main conveners for that. Before that, that's Eugenio's first postdoc. He was in Europe in a very new theoretical institute in Denmark, CP3, and it's a really cool one. So if you check out the website, and they have a lot of videos and everything theory, no experimentalist, or maybe a little bit phenomenologist. So he will talk about model-independent comparison of dark matter, mainly direct detection data, but he has worked also on effective theories, effective Lagrangian.
Kind of.
Okay, you can correct me. And then also related to dark matter before. Yes. Okay.
All right. Thank you, Emilia, for the presentation. Thank you for inviting me here. I'll try to keep this informal since I already met many of you, and actually I think some of the stuff that I will tell you about today might be interesting for some of you from what I've heard. So yeah, if you have any questions, just interrupt me at any time, please. Okay, first the title, model independent. Here it means two things, and indeed the seminar is divided in two parts. In the first part, I will apply this expression, model independent, to kind of particle physics. So I will explain what we did when to try to avoid a specific, taking into account one specific model for particle interactions between the dark matter and the nucleons. In the second part, instead, I will talk about halo model independence, so more like astrophysical properties of the dark matter. So how to set bounds and compare the direct detection data without having to assume a specific model for the halo or a specific velocity distribution for the dark matter. This is my favorite motivation for why we know that the dark matter is there. If the dark matter was not there, as you, I guess all of you know, we wouldn't have enough gravitational pull to put our galaxy together by now, so we wouldn't exist. There are several others evidences for the dark matter, which I won't go over because I'm pretty sure you already know everything. So let's start with the assumptions that I will make for this seminar. I will talk about WIMPs. So these are scale interacting dark matter particles, which are non-relativistic and with mass roughly between 1 GeV and 10 TeV. And actually, I will consider that there is only one kind of particle. So dark matter is only one kind of particle. This would be like approximating the whole standard model as just hydrogen in the whole of our, the space that we know, the universe that we know, which actually might not be such a bad approximation. So we hope that also this assumption is not that bad, but it doesn't need to be. It may be very bad. Okay, this is a brief review of how direct detection experiments work. We basically build a detector, and you put it below a mountain or underground so that it is screened by cosmic rays, and you wait. You wait, and the detector counts some hits. Some dark matter particle arrive and hit the nuclei in the detector, and what you count is this recoil rate with respect to the recoil energy. So the rate is proportional to the target density, so how many nuclei you have in your detector, and the flux of dark matter, which is in turn proportional to the dark matter local density and to the dark matter velocity distribution in the Earth reference frame. And finally, the rate is also proportional to the probability of interaction, that is the scattering cross-section, the differential cross-section. So if I expand that equation here, this is how it looks like. Actually, to be more precise, we also have to take into account the experimental effects. So we want to take this function together also with detector resolution and efficiencies. So in the end, you will have this rate here. After you convolve this, the true rate, let's say, with the experimental effects, you have the rate. This is more similar to what the experiment actually measured. You have a sum over all the isotopical composition of your detector with several integrals and all these functions here. Now, if you do this and you apply it to the actual data from the experiments, you find this situation. There are several experiments which have a signal. So there are 4 experiments with signal. These are DAMA, Cogent, CREST, and CDMS with the silicon detectors. They see some events in the detectors that can't be explained with the background assumptions alone. So they say, okay, maybe we are seeing the dark matter, and they plot their allowed region, their favorite regions in this WIMP mass versus scattering cross-section with a nucleus parameter space.
The CDMS is recalling the result, I think, soon. They found a problem, yeah.
Oh, they found a problem. Oh, this makes it
Two
so much
detectors
easier
are
for
short
me.
in it, so if they remove these 2 detectors, the signal goes away.
Isn't that the germanium?
No, the silicon.
In the silicon.
That was the silicon?
I just heard about this, yeah.
Because they had 3 events, right? And I think that you're talking about the email from Vic.
Yeah.
I don't think that was regarding this. I could be wrong, but I don't know.
But germanium didn't have an excess, did it?
That's right. Well, no, they had some events. But
They had some events.
Then they said, okay, they're consistent with background.
In which experiment?
Okay,
CDMS.
now we're confused, sorry.
But you mean, okay, a super CDMS or
That's silicon.
Um,
This is silicon, I know, so now I'm confused which is that they were going.
I'm pretty sure, yeah, okay, I mean, we can look
But
together.
there's something happening with CDMS. Is the point.
okay, very good. Well, then I will need to change my conclusions on the fly, which is nice.
Just recalculate right now.
Yeah. All right, so there are some experiments which don't see anything. These are lux, xenon, most notably there are many. The ones that put most important bounds are these lux, xenon, and also CDMS with the germanium detectors. And actually we can zoom in the low energy region. As you can see, all these regions are around 10 GeV for the dark matter mass. So we can zoom in and we get this. There are also some other bounds that I didn't have in the previous slides. This is a CDMS light, again from the super CDMS collaboration with the germanium detectors and super CDMS. So the situation is quite constrained. There are 2 problems indeed that one can see from observing this kind of plot. One is that all these regions, they don't quite coincide, so they have signals, but if there is dark matter, they are not seeing the same thing, if this is dark matter. And the other problem is that they are all ruled out by the experiments that don't see a signal by several orders of magnitude sometimes. So this is a problem, and people have tried to understand what's going on here. When you try to understand what's going on behind this plot, you have to understand what are the assumptions that people make to produce this kind of plot. And actually there are 2, there are assumptions, and these 2 are the ones that I consider major assumptions. One is that they consider only this specific interaction, kind of interaction that is called a spin-independent interaction, which in quantum field theory language can be given by these Lagrangians. They all give the same result in the non-relativistic limit, which is the one that we are interested in. And the second, so this is for regarding the dark matter particle interactions. And the second big assumption is that they consider, they take a specific form of the dark matter velocity distribution. So they assume that the dark matter has thermalized in the halo, so the velocity distribution is a Maxwell-Boltzmann, which is truncated at the escape velocity from the galaxy.
What is the phi versus chi?
So yeah, this is a scalar and this is a fermion.
Okay.
Yeah.
Okay.
Yeah. So if you want to understand what's going on in these plots, you want to try to change this assumption and see if something changes. If you get to a different result. Now, in the first part of the talk, as I said, I will cover, let's say, this part. So I will speak about particle interactions. In the second part, instead, I will cover this one. I will talk about how you can do this job without assuming a form for the velocity distribution. Are there questions so far? Okay, so if you give up the assumption that the dark matter interacts with these very specific spin-independent interactions, then you can come up with any other interaction. There are examples of operators, Lagrangians, that people have considered in the literature. These are called effective operators that you can, for instance, obtain when the interaction of the dark matter with the nucleons is mediated by a heavy particle, and then you integrate out the particle, and this is likely what you get. Or otherwise, you can also consider electromagnetic dark matter, that is dark matter with electromagnetic properties, which could be either a small charge, electric charge, or a dipole moment, a magnetic moment, electric dipole moment, also an anapole moment, and so on and so forth. Now, there are so many interactions. One might wonder. You can basically write one single paper on each of them and try to see if, assuming a different interaction, you get a better result. Maybe, though, you can do better. That is, maybe you can find a way to treat all these interactions on the same footing. So, creating a framework in which all these interactions can be treated in the same way, more or less. This was put forth in this paper. These guys created this framework, which basically consists in not seeing the problem from this quantum field theoretical perspective, because when particles are non-relativistic, maybe the quantum field theory, quantum fields are not the right degrees of freedom to consider. Indeed, when you have a non-relativistic theory, it might be better to consider something that is more similar to non-relativistic quantum mechanics. So you can have this Hamiltonian or Lagrangian or matrix element here, where now the degrees of freedom are the spin of the nucleon or of the nucleus, the spin of the dark matter, the exchange momentum, and the initial velocity of the dark matter. If you consider these degrees of freedom instead of the fields, you have basically these many operators that you can build with these degrees of freedom. Actually, there are 4 more, which were not considered in that paper, and I will also not consider them here. So the total number of operators that you can build with these 4 degrees of freedom is 16, times coefficients that might depend on the square of the momentum, exchange momentum, or the square of the velocity of the dark matter. Okay, so how do you go from this slide, this one, to this one? Well, you do a non-relativistic expansion. If, for instance, the dark matter is a fermion, you open up the fermion, the spinor, and you do this non-relativistic expansion. So for small p, and in the end, this is you can put this the matrix element in this form, with these operators. So these O, I, and R are the non-relativistic operators that are listed here. So you can see that the nucleon, the interaction amplitude with the nucleon is just a linear combination of these with some coefficients, and these coefficients are determined by your underlying theory or model. And in the end, what was done in one of these papers was to also take into account, so for each of these operators you will have a different nuclear response. So the nucleus will respond in a different manner if you have this interaction or this interaction. So the authors of this paper, they tabulated all these responses, nuclear responses, into these F functions, which are called nuclear form factors, and give this simple formula to obtain the dark matter nucleus amplitude squared, which it is not, in principle, it is not easy to derive, because what you can use quantum theory to compute the scattering cross-section of a spin 0 or spin 1/2 dark matter particle with another spin 0 or spin 1/2 or spin 1. But if you have higher spins like nuclei, you don't really know how to treat those in a quantum field theoretical language. So here you have really a very easy recipe to get the total dark matter nucleus cross-section in terms of these form factors that are all tabulated. Well, many of them are tabulated.
So what's MT?
Sorry, MT is the target mass. MT is the target mass,
okay.
so the nuclear mass, this is the mass of the proton. So yeah, so we have this formula. This easily accounts for all the nuclear physics, which is, again, complicated to compute, but these guys did the job for us. Basically, what you have to do, instead of computing the cross-section yourself, you just need to work out these coefficients from your model, and then the cross-section is basically given, and you can play with it.
So is this the result only for spin independent or also for spin?
No, this is valid for everything. These are, so this is what is usually considered the spin independent operator. O4 is the spin-dependent operator. You see that depends on the spin of the nucleon, that then becomes the spin of the nucleus. But you have also all other sorts of operators. This also, for instance, is spin-dependent, but people usually don't care about this because it is suppressed by the velocity of the dark matter, which is a small number. But if you don't have these and you don't have these, then you have to consider higher orders. And for instance, if you consider like electromagnetic dark matter, like anapole or magnetic moment, you have many of these operators together in the same cross-section. You don't have only this one or that one. You have a sum of these.
What would Q be, the lowercase q? This is, so like O10, for example, or yeah, O11.
Yeah, this is the exchange momentum.
Okay.
So this is proportional to the recoil energy of the nucleus.
So should I think the overall factor, the MT over MN square is a A square enhancement?
Yeah.
Thing?
Yeah.
I see, but I see, okay.
I thought the A squared enhancement comes from that's not, I don't think that was associated with the mass, that was associated with how many, you just get that from the matrix element.
Well, yeah, but this depends also on how you normalize.
Yeah,
these guys.
also normalization.
So, well, yeah. Well, this might simply be another way to write the A square.
But you don't get that.
No, okay. You know, I think actually he's right, because I think these guys are actually normalized already to A square. So you have one form factor for each choice of proton and neutron. So for two protons, the spin independent will be normalized to Z square. For two neutrons to A minus Z square. So the normalization is already here. This is just some factor. I probably cancel out in the definition of the cross-section. But yeah, and this is not the A square that you usually have for the spin independent.
Right, because spin dependent, you don't have it.
That's right. Well,
Yeah,
but still again,
that's
it depends
actually
on how you normalize this.
why
but-
I asked this.
Yeah, so this is not the usual a square factor. It comes from something else. I think it is taken into account when you consider the I don't remember now, but yeah, it might also be how you define this is. I don't remember.
I mean, it's kind of funny because there have been some traditional formalisms and notations for the last 20 years, and now these are starting to get changed as more and more theorists get interested in this, I think, more generalized and whatnot. So
Mhm,
it's
yeah.
a bit confusing sometimes.
Yeah, because well, yeah, but the problem is, I mean, from my perspective, the problem is with the usual formalism, you don't get an answer. I mean, you compare the experiments and they are all, it's a mess. So that's why you want also to try doing things in different ways. Which I can anticipate it won't work out in any case, but. All right, so here I summarize all the equations again. Okay, I think so. I think this is actually from the definition of the C's. So because the C are defined for in the dark matter nucleon cross Lagrangian, and this is a kind of normalization to take into account the fact that this is not a nucleon but is a nucleus. But yeah, anything. I mean, all these factors are taken into account in the right way in the end. So this means that here you have, if you consider like pp bar, like proton, like chi bar chi p bar p, right? These will give the mass of the nucleon. So p bar p will give u bar u, which gives, when you take the trace and all that, will give the mass of the nucleon. But what you are interested in is actually the mass of the nucleus. This would normalize it to the right factor. If, for instance, you have a spin 1/2 nucleus, you can work out this factor, and it is actually empty square. But here these C's are from the nucleon level, so you can only get M nucleon from here, and so you have to cancel this M nucleon from here. So basically, this takes into account a certain normalization that these are supposed to have in the nuclear case.
I guess if you were to write it in terms of partons, you would have a different factor up there too. It would just, yeah.
Well, in
It's just
terms of
normalization, yeah.
partons,
Because that the CI is just
Well,
some over parton.
well, my way to see this, yeah, exactly. So this is valid, and I would derive my CIs as a term as a function of the
So you
parton
have a
stuff.
different kinematic form factor up or factor up.
Yes, yes. So, but those just change my CIs. So this doesn't change only from my perspective. I mean, I wouldn't consider the whole Lagrangian from the partons. I would consider the whole Lagrangian from the nucleon, and then work out only these coefficients from the partons, which is the only thing that I think changes. All right. So this is what Huxton and his friends did. Now, what you can do is actually write in the cross section in terms not only as a function of these form factors, which only include the nuclear physics, but you can actually integrate these form factors with taking into account the experiment design and also the astrophysics. So you can plug in here the Maxwell-Boltzmann, for instance, and integrate all these form factors and obtain these integrated form factors, so that in the end the total rate for an experiment will be given in this very simple way as a linear combination of these integrated form factors and these coefficients. Now the nice thing here is that you don't have the problem of computing all these integrals again. I mean, you can compute them once, and then you have these, and these are always the same for each interaction. So you can change interaction. The interaction will, the Lagrangian, if you want, will only change the coefficients, but will not affect these. So once you compute these, you're done. And all computing the rate for an experiment for a fixed for a fixed interaction will be very fast. You don't need always to do these numerical integrals again, which is very time consuming. So again, from a particle physics perspective, this is factorizing fun because you put all the stuff that you are not interested in these integrating four factors. So the nuclear physics, the experimental physics, and the